I am Amal El-Ghazaly. I'm an assistant professor in electrical and computer engineering here at Cornell. And I study how we can use magnets to make electronic systems much more versatile. So what that means is how in any situation or wherever we are, they can reconfigure themselves to perform wherever and however we want to interact with them. So if you can imagine, can your touch screen on your phone deform in 3 dimensions and display what you want to see visually on it, but also interact with it physically? We can define the touchscreen topography with small magnets and control where and how much the tactile display deforms upward by controlling the local magnetic field at a very small scale.
So our goal is to integrate an array of these magnets into a display so that it can provide touch or textural feedback to the users when they're interacting with their computing devices.
Or can your cell phone still communicate whether you're in a city or in a rural area or in a forest or a mountaintop? To be able to communicate in each of these scenarios using a single device requires versatility, meaning it requires that the device be very tunable and adapt to different communication channels or radio and microwave frequencies, all in the same compact form factor for a portable handheld device.
We are currently integrating the state-of-the-art nanomaterials into microwave circuits. And so we can make those chips, what you see every day, to make them more compact, to make them more flexible. So these are the microparticles. We synthesize the nano chains. So you can see the black precipitate here. So if we attract it by a magnet, it will move around, as you can see.
Believe it or not, all of these things can be done by the little tiny components that are inside of the electronics, and in particular, by the magnetic aspects of them. We are also exploring how to make sensors that can detect the quality of crops in the agricultural field. One of the beautiful things about magnetism is that it acts at a distance, and that means that magnetic fields can penetrate through objects that we can't actually see. If we use these magnetic fields to interact with an agricultural crop deep in the soil and excite a feature in it, then we can also detect the magnetic signal from above ground, all without ever uprooting the crop.
So I'm kind of using the same principle in order to non-destructively measure the water quantity present inside tubers. Just like you see a very big coil in NMR setups, I have one more very bigger coil over here. When I close this lid, we are making the environment inside this box free from any external magnetic field that is present outside.
And we are using magnets and magnetic fields and electronics to sense what can't be sensed by other things. With magnets, you produce the signals, you produce the electronic interactions without any connections whatsoever. And that's the beauty, and that's what shows how powerful magnetics can be.